Welcome back to this explainer, brought to you by Forge College. Today, we're grabbing our technical pens and rolling out the blueprints. We are literally going to draft the architectural plans to turn that massive, monolithic EVM mansion of yours into a sprawling, hyper-efficient Solana campus. If you've been following our capstone series, you already know the deal. Making the jump from Ethereum to Solana, it's not just copy-pasting code. Oh no, it is a fundamental shift in how you think about space, state, and structure.
Okay. Let's take a quick look at the agenda before we pour any concrete. We'll be looking at the overall blueprint, mapping the EVM to Solana, drafting those account layouts, figuring out PDA seeds and authority, running through migration scenarios, and finally, getting that design map completely finalized.
So, Section 1, the architectural blueprint. Time to turn our high-level ideas into actionable design.
We are shifting from theory to a concrete blueprint now, and this really highlights the core difference we have to tackle. Think about Ethereum for a second. You basically just toss all your variables into this implicit, bottomless storage basement, let the EVM sort it out, and, well, usually charge your users an absolute fortune for the privilege, right? But Solana requires a totally different mindset. It's an explicit, fragmented model. Think of it like a hotel where every single room pays rent. You have to declare the room's exact size, who owns it, and keep a positive balance just to keep the network landlord happy.
To pull off this shift without a hitch, here's our master engineering checklist. This is how we map your EVM contracts right over to Solana program responsibilities. First, inventory the storage. 2, decide who owns what. 3, define those program-derived addresses, or PDAs. 4, write out your data structures. 5, map the executable instructions, and 6, plan out the actual data migration. Honestly, if you skip these steps and just dive headfirst into coding, your building's going to collapse the second your users try to move in. Moving right along to Section 2, EVM versus Solana mapping, where we translate that storage.
First things first, we've got to inventory and precisely translate those critical Solidity storage slots into our new Solana paradigm. You're going to want to draft a mapping table just like this one. It helps you decide if an EVM contract translates into a single program-owned account or if it needs to be split up into multiple PDAs. A good rule of thumb here, if the data is global and pretty small, a single account works great. But if it's per-user data or some massive list, you're definitely going to split that into per-user PDAs. This table right here, it literally becomes the absolute source of truth for your whole migration.
Next up, Section 3, drafting your count layouts, which is all about sizing things up in bytes.
Once you know exactly what accounts you're going to need, you start sketching out their precise shapes. And by that, I mean you start talking in bytes. Let's look at an anchor proposal struct as an example. The absolutely crucial thing here is to annotate your structs with exact serialized byte sizes. Why? Well, dynamically resizing accounts on Solana after the fact is going to make your compute complexity and your costs absolutely skyrocket. Writing out an explicitly commented 32-byte public key or an 8-byte integer right now, that saves you massive headaches and a whole lot of painful Rust debugging later on.
And getting those byte calculations perfect leads us right into the rent-exempt threshold. You can think of this as the absolute minimum balance of lamports, which are just tiny fractions of a Solana token, required to keep your beautiful new account alive and safe from network eviction. Because if you underfund an account, the network will literally just garbage collect it. Boof! Gone forever. Your users' data just gets evicted out onto the streets.
Because of that brutal reality, you need to calculate detailed rent estimates to avoid any nasty runtime surprises. For context, a 256-byte proposal PDA will run you roughly 89,000 lamports just to stay rent-exempt. Bump that up to a 1024-byte ledger PDA, and you're scaling up to about 350,000 lamports. You've got to bake these costs directly into your smart contract logic. You have to ask yourself, does the protocol pay this rent, or is the user footing the bill?
Let's jump into Section 4, PDA seeds and authority, which is all about controlling access.
Okay, so we know how big the rooms are, and we've made sure they've paid their rent, but who actually holds the keys? Enter the program-derived address, or PDA. It uses a deterministic seed tuple to securely control upgrades and act as an authority figure. Instead of relying on a user's private key to sign things, a PDA actually allows your Solana program itself to sign for transactions. By deriving the address using totally predictable seeds, you guarantee that only your specific program has the power to authorize state changes. It's a really elegant lock and key system.
And while you're busy designing these PDAs, I really need you to burn this golden rule of Solana architecture into your brain. Favor explicit account ownership and small fixed-size accounts when possible to reduce resizing complexity. Seriously, if you've got a massive array of users over in Solidity, do not, I repeat, do not try to cram them all into a giant array in a single Solana account. Instead, spin up a small fixed-size PDA for every single user. Keep it flat, keep it predictable.
So, the blueprint is looking totally flawless. The structures are sized perfectly, the keys are minted, and the rent is all calculated. But that leaves us with the multi-million-dollar question. How do we actually move our users' heavy furniture? You know, all that live, existing EVM data. How do we get it into the new building?
Which brings us to Section 5, Migration Scenarios. Let's make a moving day plan.
Look, moving data cross-chain is inherently super risky. So your architecture document absolutely requires a rock-solid moving day plan. You've got to outline a specific strategy. And you basically have three main options here. You can do a massive bulk snapshot to script everything at once. You can do an on-demand, lazy migration where users unpack their own state using Merkle proofs as they interact. Or you can go with a hybrid of the two. Each of these carries totally unique downtime and compute cost risks, and you need to document those risks right now.
Oh, and a quick pro tip for your structs here. Whichever migration scenario you end up choosing, always include a schema version tag, like a simple 8-bit integer, for instance. Why does this matter so much? Because eventually, you're going to need to upgrade your Solana program too. By tagging every single account with a version number today, you ensure that your future state transitions stay perfectly deterministic. It's exactly like slapping a barcode on your moving boxes, so you always know exactly what era of data you are looking at.
Finally, we've arrived at Section 6, finalizing the design map and wrapping up our blueprint package.
Let's do a quick review of what your finalized blueprint package actually needs before we even think about opening up our Rust compiler. Let's run the checklist. Is your mapping table totally complete? Are your example layouts annotated with exact byte sizes? Have you recorded your PDA seeds to lock things down and prevent hacking? Are your instructions mapped out and your migration risks fully assessed? If you can confidently check all 5 of those boxes, then your design is officially ready for peer review.
I really want you to remember the most important takeaway from all of this. Explicit architectural drafting right now prevents massive, incredibly expensive bugs later. Taking the time to draw precise schematics, debate byte sizes, and argue over PDA seeds today on a piece of paper, that is a whole lot easier and drastically cheaper than having to tear down structural Rust code on a live network later. You're building a campus that's meant to scale to thousands of transactions a second, so the foundation has to be perfect.
And that perfectly sets us up for our next phase, actually getting our hands dirty and building out the core program logic in Rust and Anchor. Thank you so much for exploring this architectural blueprint with me today. Remember to visit forge.college to learn more about this subject and dive deeper into other Web3 topics. You've got your blueprints and you've got your byte sizes, but remember, once this code goes live, the blockchain is totally unforgiving. So will your migration be a seamless, stress-free move or a structural collapse just waiting to happen? Stick around and I'll see you in the next explainer where we finally start writing the code.